Hello everyone and welcome to Maven Silicon. In today's video, I'm going to walk you through the concepts of memory management in operating systems and its role in the system performance. Memory management is one of the most important responsibilities of an operating system because it determines how efficiently RAM is used when multiple programs ran at the same time. Every application we use, such as browser, editor, or background services, need memory to store an instruction and data. The operating system must ensure that each program gets the memory it needs while also preventing programs from interfering with each other. In this video, we will explore why memory management is necessary, what problems occurs without it, and how modern operating systems solve these problems. Introduction to memory management. Memory management is a fundamental function of the operating system. It controls how RAM is allocated, tracked, and released for different programs running on the computer. Whenever a program starts, the operating system allocates memory to it. When the program finishes executing, the memory is freed and becomes available for other programs. Another important goal of memory management is maximizing CPU utilization. If memory is managed efficiently, multiple programs can remain in memory at the same time. This allows the CPU to quickly switch between programs and keep the system responsive. Without proper memory management, programs could overwrite each other's memory, which would cause system crashes, corrupted data, and unstable behavior. Here, we will see the relationship between the operating system, RAM, and the programs. Instead of allowing programs to access RAM directly, the operating system controls how memory is allocated. Programs request memory from the operating system, and the OS decides where in the RAM the data should be placed and allocates the memory. This control ensures that memory is used efficiently and safely. Once the program is done executing, it will be removed from the RAM. Without this layer of control, multiple programs could attempt to access the same memory location, leading to unpredictable results. Now let's imagine what happens if programs were allowed to directly access the physical RAM. At first, this might seem simpler. However, it introduces several serious problems. Since all programs share the same space, there would be no protection between the processes. This will lead to multiple issues such as security risk, memory fragmentation, physical memory limitation, wasted system resources. Let's examine these problems one by one. The first problem is the security risk. Here we have a RAM and the programs. The programs request memory from the operating system and the operating system allocates memory to them. Each program can access its own allocated memory region. However, there is no mechanism of preventing a program from accessing another program's memory. This means one program could override the content of another program. Without such protection mechanism, a malicious program could access the data of another program and steal its content, or it could directly modify the operating system, and changes could take place. Another issue is the external fragmentation. External fragmentation occurs when memory becomes divided into small scattered free spaces. This happens when programs are repeatedly loaded and removed from memory. Although there may be enough total free memory available, the memory may not exist as one continuous block. As a result, a program that requires a large block of memory might fail to load even though enough memory exists overall. In this example, the system has 1 GB of RAM. Several programs are running and occupying different memory regions. When one program stops, it leaves behind a gap in the memory. This scattered pattern of free space is what causes fragmentation. Here we can see the actual problem. The system has 474 MB of total free space. However, the memory is divided into smaller blocks. Because of this, the system cannot load a program that requires 350 megabytes of continuous memory and therefore rejects it. Memory limitation. Another limitation comes from the physical size of RAM. Every system has a fixed amount of installed memory. For example, the older 32-bit system can address only up to 4 GB of memory. Once the available RAM is fully used, additional programs cannot be loaded. This creates a limitation on how many programs can run simultaneously. This problem also exists in modern systems. Even though RAM size have increased, newer programs demand more memory compared to the older ones. Wasted resources. Another inefficiency occurs when programs load duplicate copies of the same libraries. Many applications rely on common system libraries. If each program loads its own copy of these libraries, memory is wasted. Instead of duplicating these libraries, it is more efficient to allow multiple programs to share the same library in the memory. Virtual memory solution. To solve these problems, operating system uses virtual memory. Virtual memory creates an abstraction of physical memory. Programs do not interact directly with RAM. Instead, they operate within a virtual address space managed by the operating system. Each process believes it has its own memory space. However, the operating system maps these virtual addresses to physical locations in the RAM. This translation is handled by a hardware component called as Memory Management Unit, also known as MMU. Fixing fragmentation and security. Virtual memory improves both security and memory organization. Instead of accessing memory directly, a process operates within its own virtual address space. In multiple processor system, each program has their own virtual address space, which is accessed. Since each process has its own virtual space, memory in physical RAM can be allocated in different fragmentations using paging. This prevents processes from accessing each other's memory. As a result, programs cannot accidentally overwrite each other's data. This isolation improves system stability and security, thus solving our fragmentation and security issues. Fixing insufficient memory. Virtual memory also helps when RAM is insufficient. For example, when your physical RAM is full, the operating system creates a temporary special file called as a swap file on the disk. Virtual memory takes care of mapping memory either to RAM or to the disk. When the program is inactive, it is moved into the swap file to free up RAM. When the data is needed again, it is moved back into the RAM, or a new program can use the previously allocated memory. Although disk access is slower than RAM, this technique allows system to run programs that requires more memory than is physically available. Paging. One important technique used in virtual memory is paging. Virtual memory is divided into equal size blocks called as pages. Physical memory is divided into blocks called as frames. Typically in modern operating system, the pages size and frame size are 4 KB. When a program is loaded, its pages are placed into any available frames in the physical memory. This means the pages of a program do not need to be stored next to each other in the RAM. Each page can be mapped to any available frame in the physical memory. The operating system keeps track of these mapping using a page table, and an MMU translates virtual addresses into physical addresses. This flexible mapping eliminates the need of contiguous memory and helps solve external fragmentation. However, paging introduces another small problem called as internal fragmentation. Since pages have a fixed size, A program may not completely fill the last page allocated to it. For example, if the page size is 4 KB and a program needs 34 KB, the OS must allocate 6 pages, that is 36 KB. The extra unused memory inside the last page becomes wasted space, which is called internal fragmentation. Optimizing with shared pages. Memory usage can be further optimized using shared pages. Common libraries used by multiple programs can be loaded only once in the physical memory. Multiple processes can then map their virtual pages to the same physical frame. This technique significantly reduces memory usage. So, the conclusion with regards to memory management is that it is a core responsibility of the operating system. It ensures that multiple programs can run efficiently, safely, and simultaneously while sharing the same physical memory. Without proper management, systems would face several serious problems such as security risk, external fragmentation, physical memory limits, and wasted resources. To solve these problems, modern operating system introduce the concept of virtual memory. Virtual memory provides abstraction layer that separates programs from physical RAM. Using mechanisms such as paging, page tables, and the memory management unit, the operating system can efficiently map virtual addresses to the physical memory. This allows memory to be allocated flexibly, improves system security, and ensures programs to run even when the system does not have enough physical RAM. Techniques such as shared pages further optimize memory usage by allowing multiple processes to share common data. As a result, modern operating systems can manage memory in a way that is efficient, secure, and scalable, enabling today's computers to run complex applications smoothly. Thank you. I hope this video helped you understand the key concepts of memory management in the operating system.